Okay, good morning. I'm actually very happy to be here. I'm a nuclear experimentalist, as some of you may know, so this will be a little bit of a different perspective. But as I will show you, nuclear experimentalists are really excited about X-ray observations. And I'll talk about that connection. So I don't know if you're all aware that nuclear physics has also a decadal survey. So these are also the different processes in astronomy and nuclear physics sort of going on in parallel. And if you look at the 2010 nuclear physics long-range decadal survey, you see that one of the 5 science themes in nuclear science is nuclear astrophysics. So it's one of the important areas in nuclear science. And if you look at the nuclear astrophysics questions that supposedly guide the science in the next decade, of those 4 questions, 2 require X-ray observations. So my point here is that there is a large nuclear science community that has this as their priority science, and they need X-ray observations to get the science done. I mean, they also need a lot of nuclear physics. And as part of this plan, on the nuclear physics side, we started building new facilities, ready-to-beam facilities, to investigate X-ray burst and neutron star physics. And I don't want to bore you with too much nuclear physics, but I want to give you some glimpse at what it is we're up to. So we're building a new facility called FRIP. It's a $730 million project, 1,400 scientists. And if you look at the science goals of this project, 1 of 10 is X-ray bursts, super bursts, neutron star properties. So all these 1,400 people are excited about X-ray observations. Now, what is it that we're building? Just very quick. So we're accelerating. We will accelerate a heavy ion beam with a linear accelerator that's folded up here. We'll slam the heavy ion onto a target, and it will produce lots of fragments. These fragments will be selected with a fragment separator, sent into a gas stopping system, and then they will be re-accelerated again to the right energies that these nuclei have when they react in astrophysical environments, for example, in X-ray bursts, which are pretty low energies. And there's a whole hall dedicated to astrophysics, and we're building a recoil separator that's actually under construction right now and keeps me really busy. And that thing can basically detect, measure reactions as they happen, for example, in X-ray bursts. The system basically selects the reaction product, so you can count how many reactions you have in the lab. So there's a big effort going on. This is the building. It's already there. There's a lot of things being built. The accelerator is supposed to be done in 2022, and then it'll ramp up. So over 5 years or so that may nicely coincide with STROBE-X. So again, to achieve the nuclear physics science goals, we are building the required nuclear facilities. So now we need the observers to build the right observatories so we can get the science done. Now, it's really important to connect the astrophysics and the nuclear physics when you want to address these science topics at the intersection. And luckily, we do have a mechanism for that. That's actually the reason we founded the Joint Institute for Nuclear Astrophysics. The purpose of this Physics Frontier Center, which has been around for more than 10 years, is to connect the different pieces that are needed to address questions like X-ray bursts, related to X-ray bursts. You see X-ray observations are part of this. Neutron stars and dense matter properties are one of the 2 major science topics that we're trying to address. Now, what is the center? It's a very large collaborative network, astronomers and nuclear physicists, 26 institutions by now in the US and partner centers across the world. It's a collaborative network with an interdisciplinary science program, but it's also a center for the field as a whole, workshops, schools, exchange programs, data, codes, and so on. And one of the questions I'd be interesting discussing is how can this help, for example, with your project. And I mean, GINA has pushed for new equipment, new facilities in nuclear physics. It has pushed for new spectroscopic surveys in astronomy. So why not the X-ray observatories that we need? Now, let me talk a little bit about the science that the nuclear physicists are interested in. It's all about neutron stars, and in particular, accreting neutron stars. That's the focus of GINA, and it's basically those three key topics that overlap with X-ray observations: the equation of state, X-ray bursts, shades, and cooling crusts and transients. And we'll hear more in-depth discussions of these in actually the following talks. I'm not going to say much about the equation of state. Basically, anything that measures the mass and the radius of a neutron star is a big deal for nuclear physicists. And if I look at the STROBE-X mass radius plot with those little blobs, that would be really amazing and would get every nuclear physicist really excited. I'm going to talk more about X-ray bursts and these cooling transients. So X-ray bursts are these thermonuclear explosions happening quite frequently on the accreting neutron star's surface. And this is the nuclear physicist's point of view of how an X-ray burst looks like. This is a chart of nuclides. I don't know if you guys have seen this before. So it's a table with protons and neutron numbers, and each sphere is a nucleus, and a certain number of protons and neutrons. And these thick squares, those are the stable isotopes, and then you can make other combinations of protons and neutrons, and those are the unstable or rare isotopes. And when you have an X-ray burst, you start with hydrogen and helium, so the colors indicate how much of an isotope is there, going sort of through the rainbow, with red being the highest. And if you ignite the burst, you can see that, wait a little bit, but the rapid photon captures and other reactions create new isotopes, and it's these rare unstable isotopes, as you can see. So it's reactions on rare unstable isotopes that ultimately generate the energy that powers the X-ray burst, and there it comes. So this is the light curve, so powered directly by these reactions. And in this reaction chain, there's some interesting things happening in this range here. The reaction sequence slows down, and that leads to a kind of extended energy production that leads to relatively long burst tails. And it's actually nuclear physics that is needed to understand this connection. It's those two isotopes that are particularly important circuit here. This one actually isn't even a square, and this one here. Turns out these slow down the reaction flow, and why do we know this? Well, we know this from experiments. Just to give you some idea, this is actually has been done at MSU a few years before I came there. So you fragment beam, produce all these rare isotopes, and identify them in the lab, and you sort of get this isotopic map in the laboratory. And these two isotopes correspond to these two blobs. And what you see is there's actually no blob here, which means this isotope doesn't exist. It's unbound. And this is a very feeble blob here, which means this isotope is very weakly bound. And it's that result that led to the conclusion that you have the slowdown here, and that maybe you can make this connection that long burst is related to this rapid photon capture process, and can then be used as a probe for hydrogen richness, for example, in bursts. Now, we have moved on since then, and that's one of the points I want to make. We're entering an era where we're trying to be more quantitative and make quantitative predictions of burst light curves. And so it's kind of nice to see how we've progressed. These are two recent experiments, so instead of just knowing that this isotope is unbound, we know now by how much. We've actually managed to make it briefly before it decays and measure the decay energy. In this isotope, we actually know now how weakly bound it is. We have a number, and that was done by injecting it into a storage ring in Lanzhou in China and measure the revolution time of the ion. And so we're entering this area of being quantitative, and obviously we need the same thing to happen on the observational side. And I have some examples here of what people have tried to do in this sort of era of quantitative analysis. This is an illustration where people have tried to have X-inverse models matching the data of this thin lag line in the background. And then there are 3 models with different surface redshifts, and they try to sort of, by matching this to the observed light curve, extract that information. That didn't work. Turns out if you fit the tail value, you cannot fit the peak and vice versa. And that actually wasn't so surprising because what we did is we looked at the remaining nuclear physics uncertainties, and we found that there are many reactions that have these kinds of effects here. There's just one reaction, photon capture aluminum 23, that's varied within its errors. And you can see that the change in the burst light curve is much larger than what we're trying to extract here. So obviously you need better nuclear physics, but you also need good data. Here's another example. It's actually a paper that just has been posted on the archive, and Lawrence is a co-author in this, where they analyzed 1200 bursts from RxDE, and they tried to fit them with some empirical model. And what they found is they need this Gaussian tail here at the end, and they interpreted this as a signature of this rapid photon capture process. And now we can play games. You can look, for example, is there a relation between how much RP process you have and the accretion rate, and they found indications of a different burning regime at low accretion rate, for example. I also thought it's interesting that you cannot do the same thing with models. So if you try to fit the model light curves with the same fit, it doesn't work. So there's something wrong with the model, and again, I think it has probably to do with the nuclear physics, and we have to fix that, and then we can maybe see if there are other things that are wrong with the models. We need accurate nuclear physics, but we also need really precise observation data on burst light curve, and you see this, and they write this in the paper. The data are very, very coarse, and they actually mention STROBE-X as kind of a big next step to maybe get precision light curves. Now light curves are only one observable. What nuclear physicists would be really excited about is having detection of a line or an absorption feature in an X-ray burst of an element that has been created by the nuclear reactions. That's sort of, I learned in one of the previous talks, you're not supposed to say holy grails, but nuclear physicists would be really excited. And there's kind of a history of tentative lines and features that have been found. There's one example here from NuSTAR. There's I think less than 2 sigma detection. This thing here, which they say could be a chromium line based on predictions from models. But the point is here that observations seem to be not there yet, and if STROBE-X could improve this situation, I think that would be amazing for nuclear physicists. This would really give you a real constraint on what the nuclear physics is that's going on. I don't know, for example, various QPOs during bursts. I don't know if STROBE-X could do like time resolved spectroscopy to get rid of the rotational broadening, and of course the large collecting area should help. So this would really be a big deal. Now, if all these nuclei are made in the burst, and they're not showing up in the observational signatures, they still do interesting things on the neutron star, and that manifests itself in these cooling transients. So as you all probably know, these are cleaning systems that shut off for years or longer, and they can be observed evolving over time, and what one sees is this amazing cooling of a neutron star over time scales of a few years. There's some data, and there are many more, and I think Craig will show you much more exciting things here. The interpretation here is that, of course, you're not really seeing a neutron star cooling. What you see is the cooling of the crust of the neutron star that has been heated during accretion by nuclear reactions and is now cooling back to the overall temperature of the neutron star. And nuclear physicists are really excited about this because as time progresses, this cooling curve probes dense matter physics at increasing densities throughout the crust. And these are some examples of what people have tried to get out of these cooling curves. There's, for example, a strong indication of an unknown heat source that we have no clue what it is, but it seems to be there at very shallow depth. There's indications maybe of superfluid neutron layers, And even this nuclear pasta, which is something that has intrigued nuclear theorists for decades, and it's kind of this completely theoretical thing at the interface of the crust and the core. And you can see here, basically protons and neutrons are not arranging themselves anymore as individual nuclei in blobs, but the protons form, in this case, these extended sheets with a neutron gas around. So this would be a lasagna phase, and then there is also spaghetti and other things. And here's actually a way, this affects the deep conductivity, and maybe signatures be found at this turnoff at the end. So there's actually maybe ways to see this, and that would be really exciting. Now, I want to focus here on one question, and that is the fast cooling. I think when people first saw these cooling curves, they were quite surprised. I think most people expected maybe 10, 20-year time scales for cooling. This is actually relatively fast, and this implies that the crust has a very high thermal conductivity, and must be a very pure crystal with only a single isotopic species, no impurities. And now you should look all puzzled, because you remember the movie with the rapid photon capture crust produces this broad range of isotopes, and that's basically what the crust is made of, right? The ashes of the bursts. So how can this be a single species crystal? Well, the idea was that somehow nuclear reactions in the crust, as the ashes gets pushed into the crust, converted, and that these conversions lead to homogenization of the composition. And they actually just carried out some calculations to explore this. And it's kind of the same movie that I showed before, same type on the chart of nuclides. But now we're seeing, these are basically the stable nuclei that have been produced in an exaburst and have now, they're producing here and they're now decayed. And now they're getting pushed into the crust of the neutron star. And we can see what happens. Maybe the composition becomes a simple single ion species composition, or maybe not. So here it goes. So as we go deeper and deeper in the crust, this composition gets more neutron rich because the electrons get high and high energies and get captured by the nuclei. And you see the composition basically moves towards neutron drift. The neutron unbound nuclei are the gray shaded things here. So you see it just moves, so there's no real simplification of the composition happening. At some point you start getting fusion reactions, which are very interesting, induced by high density. I'll just keep it going. With those, you start getting the first simplification, but still not much happening. The big hope was actually that when you hit the neutron drift line and you get electron capture, neutron emission reactions, that those will simplify the composition, and they do. And it turns out this inner crust, where we sort of arrived now, is what matters most to explain the cooling curves. So, so this is good, but it's actually not really that good, because there's still three different isotopes, right? And they're quite different. So this would not be a high conductivity crust. And we found this quite interesting. I don't know if you know what these lines are.
Magic numbers?
Yeah, those are the magic numbers. So those are the shell closures. And those nuclei are particularly bound, and the composition sort of gets stuck in those shells. And so the question is, does this shell structure exist at the neutron drift line? And maybe those X-ray observations are first hint, maybe during some nuclear physics here, that shell structure disappears at the neutron drift line. This actually has been a theme in nuclear science for a long time. And there are actually indications here. This is the closest to stability, so there have been some experiments here. These have never been studied in the lab, but there have been some experiments here that seem to indicate a disappearance of the shell structure. But other shells may appear, and so that's still an open question. So the good news is that this effort facility that I talked about will be able to study pretty much everything that matters in creating neutron star crust. So again, we're going to have the data from EFRIT, and then we'll need data from cooling curves. More data are good because, as Craig will show you, there's a large variety of systems that behave differently, so it'll be really important to get some statistics on that. It's important to catch the cooling early to get more information on this shallow heat source. And of course, I think what's in my mind also important is that the crust is made of sort of the entire outburst history prior to the quiescence. And the more you know about that, the better. Ideally, you would have sort of a complete history of the source, like what kind of burst did it have super bursts or not, until so complete coverage. Anyways, so I have my conclusions. So point one, there's a large nuclear community with interest in X-ray observations, and I would think that could be useful. If not anything else, it is an additional motivation. People want to understand the nuclear processes, and that's what you provide important data for. There are these sort of three major areas where X-ray observations are needed. There are major investments being done in isotope research, partially motivated by the science that also requires X-ray observations. So I would think some coordination across fields may strengthen the cases, and that'll be interesting to explore. I'm not sure it's about money necessarily. I'm not sure interdisciplinary research means you sort of tap into each other's pods. But still, I would think that, all things being equal, if you have two astronomy missions and one has this broad impact on another community, that may be an argument for the agencies. And then I want to remind you again that Gina is there to provide this link between nuclear science and astronomy. X-ray observers are actually part of GINA. Some are. Ed and Lawrence have been part of GINA for a long time. There are workshops planned. There's a CROSS workshop, for example, in November in Seattle, and there will be an X-ray burst workshop in 2018 in Italy. So I think it'll be nice to discuss, how can this network be helpful. I, for example, saw you want to show posters at the AAS. Should there be a nuclear poster there? Those are things we could talk about.